How strong is that acid? Wait, where's the base? So today I thought I would do a post on acids, bases, and pKa, which is a measure of how strong of an acid something is. And as you'll see, acid and base are really just two sides of the same coin. And so first I will talk about things with a fun Cookie Monster analogy, and then a more formal molecular look at what's actually really going on. So let's start with the fun analogy. So imagine that you have a party and you have a jar full of cookies. So you have a cookie jar and you invite over some friends. So some of the friends bring cookies and they donate cookies to the jar. And some of the friends don't bring cookies but they come hungry, and so they just take cookies from the jar. At the end of the night, how many cookies are in the jar is going to depend on how many of each type of friend you invited. So how many people came with cookies, how many people didn't come with cookies, and how greedy were the people. So we can think of something similar happening with pH. So in the case of pH, what we have is that we have this like proton jar. And so we think of our cookie jar as now a proton jar. And the fuller this jar is, since these are protons, that if you have more protons, that's a more acidic solution, which, as we talked about yesterday, means you have a lower pH. So a lower pH means more protons and more acidic. And this is because the pH is the inverse log of the concentration of protons. And so these brackets mean concentration of. So because you have this log over one, this inverse log thing, if you have a bigger number of protons, so a fuller cookie jar, you're going to have a lower pH, more acidic solution. Okay, so why does this matter? Well, depend how greedy those cookie monsters are. So some of the cookie monsters, say even if all the cookie monsters came with cookies, they're not all going to be as willing to share their cookies. So some of them what we call strong acids. And basically, it doesn't matter to them, like if the cookie jar is already full, they're just like overfill it, right? Because they're super, super generous, not greedy at all. They don't want those cookies, they came to share them. But for other people, they might see that cookie jar and be like, oh, that's pretty full already. Like if people want a cookie, they can take a cookie. They don't need to take my cookie. And so they'll hold on to their cookie until maybe the level gets really, really low. And then they'll be like, okay, maybe I should let someone else have my cookie. So it's not really that way biologically, but biologically what's more happening is that if you like lose your, if you give up the cookie, then if the jar is empty, you're less likely to find a new cookie to take again. So if a molecule loses a proton, then it's going to be less likely to find like another proton to bind to. So even if it wants a proton, there aren't many protons around, so it's not going to be protonated when you go to measure it. Whereas if one is really, really wants that proton, if it's it's less likely to give it up, and if it does give it up, it's going to hold on really, really, really tightly to it if it finds it one again. So even though there might not be that many, since it's less likely to like let go, then it is more likely to be bound. And so a strong acid is something that is going to donate no matter what. So like technically like a strong acid, what we say is it like completely dissociates. And so by dissociate, what we're meaning is like, in this case, we're talking about it deprotonating. So you're separating that proton from the rest of the molecule. And so a strong acid is going to completely dissociate. So like hydrochloric acid, you put it into water, it's going to, all those protons is going to be lost to the water. But so what about water? Well, water is actually a weak acid because, as we showed yesterday, it can actually deprotonate to form a hydroxide ion and a hydronium ion if that proton then binds up to another water molecule. Another weak acid you might have heard of is like acetic acid. And so it will partly it will exist in both the protonated and deprotonated states. It's not fully dissociating. And then on the other hand, we have what we call strong bases. And so basically, the way you can think about it is an acid and a base are really just two sides of the same coin. So if you have an acid and it gives up a proton, well, now it's able to take a proton, which means that it can act as a base. So an acid in this definition of an acid and base, an acid is something that will donate a proton and a base is something that will accept a proton. pKa is a measure of an acid's strength. So basically, how low does that cookie jar have to be before they will donate? And since we have that inverse log relationship, this means that below this, so the pKa is the point at which half of it will be deprotonated, or at the individual molecule level, if you take like, were to randomly choose one of these molecules of this acid, say, it would have a 50-50 chance of being protonated or not protonated. And then at the like bulk level, like half of it would be protonated. And so if you think about what would happen, so if you had a low pH, so you had a really full cookie jar, you would be more likely to find them with the cookie, right? So they see the cookie jar is really full. Why should I donate my cookie? Or if you don't like thinking about it that way, there's just a lot of cookies around. So if I donate a cookie, there's plenty to take right back. So if you are below the pKa, that means you have more protons, remember, more cookies. So the cookie jar is more full. If the cookie jar is really full, you're more likely to find it protonated. So below the pKa, an acid is more likely to be in its protonated form. At the pKa, then you'll see it 50-50, like it's kind of like on the fence about whether to donate. Above the pKa, at this means, remember, because you have that inverse relationship, so above the pKa, you're going to not have many protons at all. And so your cookie monsters are going to be more likely to be deprotonated because there are fewer cookies around. So even if they normally really want a cookie, they can't find a cookie. So above the pKa, you're more likely to be deprotonated. Below the pKa, you're more likely to be protonated. And at the pKa, you're kind of 50-50. And so the pKa is measuring the greediness of that individual cookie monster. So the pH is measuring at the global level of this entire solution. But the number of cookies, remember, the pH is going to depend on all of those cookie monsters that you invited to your party. So all of those friends that came to your party. And then the strength of the acid, the greediness of those individual friends, that's the pKa. So if something has the lower the pKa, the stronger the acid. So remember, a low pKa corresponds to a fuller cookie jar. So this means that even though there are a lot of cookies around, you're still less likely to find it with a cookie. And this means, since we have this acid base in the conjugate acid of is the like acid form of a base, and then you give up and then you're a conjugate base. So these are two sides of the same coin. So the stronger something is as an acid, the weaker its conjugate base. And so, so that's kind of one of the ways where you can help determine how strong of an acid something is going to be. You can kind of predict it. So if it's based on like how stable its conjugate base would be, say, or how happy its conjugate base. And by weaker conjugate base, that means it's less likely to take that proton back, right? And so if you have a stronger acid, it usually it's happier in its base form, right? And so maybe it's like better able to stabilize the, like not having that proton or that sort of thing. So if you have a strong acid, it's going to have the stronger the acid, the lower the pKa, and the weaker the conjugate base. The weaker the acid, the higher the pKa, and the stronger its conjugate base. And you can take this to the extreme where you have a really high pKa. That means you have a strong base because they're flip sides of the same coin. And if something is so remember, the higher the pKa, that means that the cookie jar is less full. So even if that cookie jar is running pretty low, it's still going to take a cookie. It doesn't really care that there are other people that want those cookies. But remember, it's really not that these molecules don't care, it's just that they're holding on to them more tightly. And so at this point, we need to talk a little more about what's going on at the molecular level. Get away from this idea of cookies, but keep that cookie intuition in your head if it's a helpful thing for you. If not, just ignore it all and let's dive into the actual molecular level about what's going on. Okay, so what is a proton? So going back to why we say, like, where do these protons come from or whatever, so more about this in yesterday's post. But basically all atoms, so atoms are like the smallest individual units of an element, so like individual carbons, nitrogens, hydrogens, oxygens, all of that, those good things that you can find on this periodic table of elements. So a hydrogen, it only has, and so atoms are made up of these smaller parts, so protons, positively charged, neutrons, which are neutral, and electrons, which are negatively charged. And so these number of protons is going to define the element. So hydrogen is always going to have 1 proton, nitrogen 7, oxygen 8, and carbon 6. But their numbers of electrons and neutrons can vary. We're not going to talk about the neutrons here. But hydrogen, it only has 1 proton and 1 electron, and in the normal form of hydrogen, it doesn't even have any neutrons. So this means if that electron leaves, then you're left with just a proton. And if you just have a proton, that's a proton. So that's why we can write proton as H+. And so the reason why you'll often see this proton is because the hydrogen atom isn't very good at holding on to that electron. And so it can leave molecules with leaving its electron behind. So molecules are formed when you have atoms sharing pairs of electrons. So for reasons that I've gone into in a different post, atoms like to have what we call this full shell of the valence electrons. So valence electrons are like the outermost electrons, and they like to have a full shell. Too complicated to go into here. But the key thing to know is that they'll share and swap electrons in order to get to their happy place, the full shell. And we can think of this kind of as like a dog walker. So the protons, they have the positive pole, and that positive pole is kind of like a leash on those negatively charged electrons. So opposite charges attract. So the positively charged nucleus is able to help rein in those negatively charged electrons. And some atoms have stronger dog walkers. So they have a stronger pull over those electrons. We call those electronegative atoms. And a great example of this is oxygen, which is really electronegative. So it has a really tight pull over those electrons. Hydrogen, not so much. That dog walker is not very good at controlling that dog. So this means that if you have like a water molecule, what you have is these 2 hydrogens are joining up with this oxygen, and so they're sharing these pairs of electrons. But because oxygen is so good at reining in the pulling in on these electrons, even though these oxygens electrons came from the hydrogen, they kind of switch their loyalty, and now if they'll stay with the oxygen if the hydrogen leaves. And the hydrogen the bond is less strong than other bonds. And so it's, especially with the oxygen, like pulling it away. And so the hydrogen is more likely to leave. And when it leaves that electron behind. So it's leaving as a proton, because remember, hydrogen is one proton, one electron. If it leaves without the electron, you got a proton. Okay. And because when it's still bound, when it's still bound, then you still get this partial separation of charges because those protons are stuck in the center of the atoms, but those electrons can move around. So even though we draw them in those shells, they're really in these like clouds that can like shift around. And so the electrons are more likely to spend time with the oxygen. So then you get this separation of charges. And so this is the basis of like a lot of intermolecular interactions, but that's not what we're talking about here. What we're talking about here is when the hydrogens actually leave, where you get that protonation. And so as we saw yesterday, we can then think of water as kind of this mix of having like water and then hydroxide ions and then hydronium ions, and then because normally when water deprotonates so it has this proton, it's going to join up with another water to form a hydronium ion. And so that's where the pH comes from, and water ionization constant and all that we're not going to get into here. But this is just to say where that hydrogen is coming from. And as you see here, it's really like this two-way interaction. So you can have deprotonation and then protonation. And the strength of an acid or base is going to like kind of dictate how bidirectional this reaction really is, like how much bigger is the left arrow versus the right arrow. And so how likely is something to give up versus take. And remember that we can define this with the pKa. So the pKa is the strength of the acid. And so we can then go back and talk about the pKa, which is where it's like half likely to be protonated, or half of it is protonated. And so basically, although we talked about the molecules as like wanting it or whatever, it's really like if the molecule is able to find a proton, and it's more likely to be able to find a proton if you have a low pH, which means you have a full cookie jar, a lot of protons. So if you have a low pH, it's more likely to find a proton if it deprotonates. And then but that's true for like all molecules. But what then determines how strong something is going to be is whether it is then likely to like hold on to it tightly. So if it doesn't like lose it, if it's able to hold on better, then you're more likely to find it protonated, even if you have a lower pH. I'm sorry, even if you have a higher pH, so like a lower proton concentration. And that's why we can define the pKa as the pKa is like a measure of the pH at which that happens, because even molecules at the same pH will have different amounts. So you can have one thing be below this pKa, while another molecule is above its pKa. And this comes into play a lot when we talk about proteins, because proteins are really like kind of like a chain of Cookie Monsters. So there are certain the various amino acids, so protein letters. So some of them can be charged some of the time. And the reason why we say some of the time is because their charge state is going to depend on the pKa. And so these have different, these side chains have different pKa. And so the overall charge of a protein is going to depend on the pH, but also on the pKa of the side chains, like the different combination of amino acids they have and how many of these are like acidic versus basic. And so we talk about like acidic and basic amino acids, but when we talk about that, we talk about what the acidic or basic in their neutral form. So for example, aspartic acid, we almost always find it as aspartate. but because it's acted as an acid and given up a proton. And the reason why we almost always find it in this aspartate, this negatively charged state, where it's actually like a base, like it can't act as an acid anymore. It's already acted as an acid, right? In the conjugate, so it's its conjugate based form. And the reason why is because you can see it has this really low pKa of about 3.7. So this means that at the cellular pH of like 7.4-ish, you're going to have it almost fully deprotonated. Because remember, the pKa is the value at which half of it would be deprotonated. And so when you're above that, you're almost all going to be deprotonated because there are not that many protons around. And so it's not likely to find one. And if it finds one, it's going to give it up right away because it doesn't really want it, right? And so that's why you're almost always going to find it this way. On the other hand, are what we call basic amino acids. And so we call the basic form is actually the neutral form. But we normally find them in their conjugate acid form, which means that they've already acted as a base, so they've taken as a proton, and now they're in this charged state, this positively charged state. And for lysine and arginine, we're almost always going to find it in that positively charged state because they have pKa's that are significantly higher than the cellular pKa. However, histidine, it has a pKa of 6, so it can be in either state. And so remember that pKa is the halfway point. So half of it would be in both forms. It's not like you go from 6 to 6.1 and now all of it is deprotonated. Instead, it's like a gradient. And so you're still going to have significant amounts in both forms at the cellular pH. And then we can define, since we have the protein is actually like a chain of these, remember? So it's like our chain of Cookie Monsters, where some of them are acids, some of them are bases. And we can define the isoelectric point as the pH at which the protein is net neutral overall. So the amount of positively charged things, amino acids, balanced out by the number of negative. And often this is the point at which a protein is least soluble. But we can take advantage of the pKa and something that I've talked about before, which is ion exchange chromatography, where we can separate proteins based on their charge. So proteins are going to be more positive at a lower pH and more negative at a higher pH. And where that balance lies is going to depend on their pi. So the isoelectric point we just talked about, where we since that's different for different proteins, then you can take advantage of the difference in charge to separate them based on this ion exchange chromatography. And I have a post on that too, if you guys wanted to know more about that. But I've been talking a lot about acids as proton donors and bases as proton acceptors. And that's actually just one definition of an acid and a base. And so that's what we call this like Brownstein-Lowry definition. So they came to this definition independently, but so we name it for both of them. So they say that a base is something that takes a proton. The Lewis definition of a base is basically that a base is is an electron pair donor. And that an acid is like an electron pair acceptor, and then it gets kind of confusing, and like, where is this coming from? So this goes back to what we were talking about the other day about nucleophiles and electrophiles. So a nucleophile is something that it has extra electrons or share of electron density. So these are often, but not always, fully negative, and they often have this a lone pair of electrons. And so they're nucleophilic. They're seeking out protons in the nucleus. They're seeking out a nucleus because nucleus is where you have those protons, and protons can help them handle all those electrons, right? The whole negative charge. The opposite charges attract, or we can think of the dog walkers reining in their dogs. And so they want some help with their dog walking, controlling all those negatively charged electrons. And then on the other hand, you have electrophiles, which are the opposite. They want more electrons, and so they make a really good pair with the nucleophiles. So a nucleophile it has this, if it has like a lone pair of electrons, now it can act as, going back to this, it can act as a Lewis base, or a Bronsted-Lowry base. And the difference is that with a Bronsted-Lowry base, this means that what you're stealing is a proton. And so this can lead to things like elimination reactions. This is what I originally made this post for when I was talking about like SN1, SN2 stuff. So if it adds to, you can act, if it acts as like a nucleophile or whatever, then it can, you get substitution, and if it acts as a base, you can get like elimination. But that's not what I'm talking about here. What we're talking about is basically that if the nucleophile can like attack an electrophile or whatever, if it takes a base, then it's kind of like a dead end because it took this hydrogen can't attach to anything else. But if it attacks something else, then you can like build on from that and make a new bond and that sort of thing. But this is why we can talk about, this is why it really isn't as confusing as it seems like it is, that a base is an electron pair donor. It can seem really confusing when you're thinking about like a base as taking a proton, but it's actually donating electrons to that proton, because the proton can only come, it doesn't come with any electrons. So the base needs to donate a pair of electrons in order to take that proton and form a bond with it. Because remember, a single bond requires two protons, and with two electrons, and the proton is just a proton. And so if you take a proton, then these two electrons are the space is donating its electrons to the proton in order to form that bond. And that is why you have these two definitions of an acid and a base, and why that can, well, I hope that helps explain some things.